Hey everyone! If you saw the last video, we built a fully functional k-means clustering algorithm from scratch. We used a fixed value of k equals to 4 because we knew how our synthetic data was generated. But in the real world, your data doesn't come with a label telling you how many clusters it has. So, how do we find the optimal number of clusters? Today, we're going to implement the elbow method. We'll update our Scratch implementation to calculate inertia and then plot it to find that sweet spot. The elbow method is a heuristic used to determine the number of clusters in a dataset. It looks at inertia, also known as within cluster sum of squares. Think of it this way. Inertia measures how tightly packed your clusters are. The more clusters you add, the closer the centroids get to the points, and the lower the inertia becomes. If every point has its own cluster, inertia is 0. The goal is to find the point where the decrease in inertia starts to slow down significantly. That bend in the graph is our elbow, and it represents the best trade-off between cluster tightness and simplicity. Let's jump into the code. First, in our init method, we add inertia underscore and initialize it to none. Now, look at this new compute inertia. To calculate this, we take every point in X, find its assigned centroid, and calculate the squared distance between them. In this vectorized version, self.centroids labels creates an array the same shape as X, but instead of the original data, it contains the coordinates of the assigned centroid for every point. We subtract them, square the result, and sum it all up. This gives us one single number representing the tightness of our current model. Next, we update our fit method. At the very end, once the centroids have converged, we call compute inertia and store that value in inertia underscore. But we don't want to manually run the model 10 times. So I've added a static method called elbow. This helper function takes our data and a range of k values. It loops through them, fits a k-means model for each, and collects all the inertia values. This is exactly what we need for our plot. Now, let's run this on the same blobs from the last video. Look at this plot. On the x-axis, we have the number of clusters, and on the y-axis, we have the inertia. Notice how the line drops sharply and then starts to level off right at k equals 4. That bend is the elbow. This confirms that for our dataset, 4 is indeed the optimal number of clusters. If we choose k equals 2, our clusters are too loose, that means high inertia. If we choose k equals 8, we aren't gaining much more clarity, just making the model more complex. And that's it! You've now upgraded your k-means implementation to be smart enough to find its own k. If you found this helpful, hit that like button, and I'll see you in the next one.